Good morning. I hope you had a great day yesterday during the presentations, and I hope it was nice in the evening as well. At least the weather was, it was not raining. You know, yesterday was the day, the warmest day in the last 40 years. Yeah, so, and that's not all. The last 3 weeks were the warmest 3 weeks in the last 150 years. So we have really exceptional time here. And today is really exceptional day. And the whole day today we celebrate 2 anniversaries. We have 50 years of software engineering, and we also have 40 editions of ICSE, and that will be visible throughout the day with plenary sessions and later on the banquet. So, as you know, for today we have now, after opening session, we will have our keynotes, and then after that, we will have a parallel session as a standard for ICSE, and then in the afternoon at 4 o'clock again, we will have a panel discussing about software engineering before and in the future. And then between 5 and 6, you will see many chairs which organized previous ICSEs and which also defined the program. So PC chairs and general chairs from last almost 50 years. So I think that will be also a very exciting moment. And then in the evening we have the banquet. So for the banquet, there will be buses starting from 6 o'clock in the front of the conference. It's in that direction, so outside. So that is the entrance for this venue, for the Congress venue. So not in front of the hotel, but in front of this entrance. And students volunteer will be there, so they will show you the way. And the buses, they will just arrive. And when the bus is full, then it will go to the place for the banquet. It takes about 15 to 20 minutes by bus. It's also possible to go by public transport. It takes a little bit more time, maybe half an hour, maybe 45 minutes, it depends. It's also possible to take bus or combination of ferry, and you can walk. There are different possibilities, but the buses are the simplest way. So when you come there, you will come first to the square, which you can see here on the picture. There will be some music and some starters drink, and so we will be outside, and later, as it approaches to, I think, about 7 o'clock, also 6:45, you will go inside that building for the dinner. So I hope you will have a great time. And starting from 10:30 up to 24 hours, there will be buses to take you back here to the hotel. What is very important, please, so don't forget your badge. Because, you know, we have one, which is actually nice problem, but we are so many. We are much more than we had expected, especially in last days, so many people, new people register, so on. So all places are filled, and there are still some people which are in queue waiting. So if you don't go for this banquet, please tell at the registration desk that you will not come, so you will free a seat for someone else. But we will try to get that everyone gets a place. But we are exactly, you know about full. All places are full fit. So it's about 1,200 people today have registered for the banquet, which is a quite high number. And then also, for you who registered but did not get a book, so after lunch, we will get new books, so you can pick up them after lunch, of course, with a book ticket. So I hope you will have a great day today. You will enjoy. And let's continue with the first speaker of today.
Okay. Good morning, everyone. It's my pleasure to give my own welcome to all of you this day on this very nice day of celebrations, 40 ICSE conferences and the 50th anniversary of the very influential NATO conference on software engineering that was held in Garmisch. I can think of no better way of starting off these celebrations than with a talk by our first speaker this morning, Fred Brooks. Fred Brooks is a professor of computer science at the University of North Carolina at Chapel Hill. He's somebody who's very well known to our community. He's one of the few people in our community who has been recognized with the ACM Turing Award. He's also the author of at least 2 very influential publications that are read not just by all software engineering students, but probably by the vast majority of computer science students as well. I'm referring, of course, to his book, The Mythical Man Month, which is a very evocative portrait of his experiences as a project manager on the System 360 and OS 360 projects with IBM. And of course, his paper, No Silver Bullet, a very pointed examination of the role of essence and accident in software engineering. As well known as he is to our community, perhaps there are a couple of things that you don't know about Fred. First of all, he considers one of the most important decisions he made as project manager on the System 360 project to be not a software decision, at least not directly a software decision, but rather a hardware decision. And that was the decision to move from a 6-bit architecture to an 8-bit architecture. This change had the significant advantage of allowing the representation of lowercase letters in the representation of text inside the system, but it also had the negative effect of incurring an expense of $100 million for IBM because it required re-engineering the full product line of I/O devices. The second thing you might not know about Fred is that he was a keynote speaker at the very first ICSE, the National Conference on Software Engineering, which was held in Washington, D.C. in the fall of 1975. And so on this day of celebrating 40 ICSEs, I think it's only fitting that we close the loop, as it were, and invite Fred back to the stage and to hear him give his unique insights this morning about the history of software engineering. So please join me in welcoming Fred Brooks.
Okay, going up. Thank you.
Okay.
Good morning, everyone. Let me set my timer. So. First disclaimer is that I've tried to get the dates right. I've done a lot of looking, but I don't promise that any of the dates are completely accurate except ones I remember myself. And so don't cite my dates. And the second disclaimer, I think, will be obvious, and that is the pictures I'm going to show of people here do not represent how we look today. There's an American story of hardship, and so I'm going to cite it, and that is, you kids had it so easy compared to the early days. When I was a child, there were no school buses in town. We had to walk to school. My walk was about a mile, and we had to walk in this rain and snow, and it was uphill both ways. So I learned to program on the IBM 701 in 1952, and then I got a summer job in 1954 programming on an IBM 701. And let me tell you what it was like. We were hand coding on paper. Then somebody punched those into cards and they got fit in the 701. We had to code in binary, but we used octal abbreviation. So both opcodes and addresses were octal numbers. The addresses were absolute addresses. There were no assemblers. And so I got a piece of roofing tile that was 64 by a ceiling tile that was 64 by 64 and some matchsticks to keep track of where the live variables were and where there were empty spaces that could be used in the programming. And then one transferred the program to, in that case, punch cards or to paper tape or to punched film, and then it ran on the machine. And with the 701, which had a mean free error time of 10 minutes, you did a rollback to drum every 5 minutes so that when the machine dropped a bit, you could pick up where you were at least no more than 5 minutes ago. And we got 2 shots a day. Now, in my abstract, I covered this ground, but I want to do it anyway, and that is make distinction between 4 kinds of programming entities. The first is a program, and the first program, as far as we can tell, well, the first program was written for the Manchester Baby, and it takes 1 page. The best known early programmer, so I'm starting with the 40s, this is the 1840s, was Ada Lovelace's for Babbage's analytical engine. Babbage didn't get the analytical engine built, but at least they got Ada got the program written. The next kind of thing is a software product. So a program is something I write and I use. A software product is something I write and you use, and it requires more work. It has to be generalized, it has to be tested, it has to be documented, and usually it has to be maintained. The next kind of entity, different in kind, is a software system, a system of many separate programs working together. And this is more work because you have to define the interfaces, and many, many, many system debugging troubles are because my understanding of at least the connotations of the interface and your understanding of the connotations of the interface are different, and they don't work. So now we have to do system integration and test. And the first example I can find of a programming system with multiple components was the GM batch operating system for the IBM 704. Bob Patrick at GM and Owen Mock at North American Aviation were the designers of this. And it had all these different components, and it improved performance on the 704 by a factor of 10. And the reason is because otherwise people were putting a job in, getting a dump out, mounting the tape, unmounting the tape. This way you put all the jobs for the whole run on one piece of tape, and the operating system would, as soon as it finished one, as soon as it finished dumping your memory because there was a divide error or whatever, then it started the next one immediately and got rid of the waste time on the computer. It also gave shorter turnaround, and there were professional operators, whereas with the earlier programming systems, you ran the machine, and you didn't know necessarily how to run the machine, and you made the mistakes in running the machine. The professional operators made their own set of mistakes, but a much, much smaller set. But there was no idle time. 40 copies were distributed among the people who had built it, but there was no support. It was not a product. And so then we come in 59 to the first software system product that I can find, and that was the Share operating system. The Share was an organization of users of scientific computers, particularly IBM scientific computers. And the Share operating system was an upgraded version of the GM operating system, which IBM distributed and which IBM took the responsibility for maintaining. So now we have a software system product, and this is the milestone. Now, software engineering, then, is the discipline of making software products, not necessarily system products, but any kind of software products that are distributed and maintained. And Margaret Hamilton is the person who coined the term, trying to make people understand that in the Apollo system, the software was much more complicated than the hardware. And so she coined the term to at least give some respectability to what it was we did, and that is the engineering. And this picture shows her in the mock-up of the Apollo cockpit, presumably debugging the software. So let me start now. I'm going to spend most of my time on the earlier parts of the period because that's the part that I remember and most of you don't. And so we'll start with the 40s. The big ideas of the 40s were machines. They were actually programmable computers. Now, Babbage's was proposed and detailed, planned, could be built, and versions have now been built in 1843. But the first of the modern computers was done by Konrad Zuse, and it was done in 41. And those of us on the outside of Nazi Germany didn't know about it. And so from my point of view, the first computer was 1944, when Aiken was the architect and persuaded IBM to do the engineering of the Harvard IBM Mark I. So this was the machine that turned me on to computers. I was 13, and I read about this in the Time magazine, and my eyes lit up, and I said, that's what I want to do. And I've been blessed with the opportunity to do that my whole entire life and to see a most amazing transformation of the world from 1944 to the present time. And then came the idea of the stored program computer, and if you have never read Burke's, Goldstein, and von Neumann's preliminary design of a calculating machine, every computer scientist and every computer science student needs to read that paper, and your mouth will fall open as you read it for the amazing amount of ideas that are important today that were packed into that very first paper. And the most important of those ideas was to store the program in the same memory with the computer. And John von Neumann conceived of the idea. Tom Kilburn and Freddie Williams at Manchester built the first working version of a little machine called the Baby that had 32 bits of memory. And Sir Maurice Wilkes, then wasn't Sir, built the first useful version of that, the EDSAC at Cambridge, in 1949. Morris is quite a character. He died at age 97. I visited his laboratory and on sabbatical, spent 3 sabbaticals in his laboratory from 1975 until 2009. The last time I was visiting, I think it was 2008, he was 94. He came into the lab many days, and it was in there every week, and we had a lot of useful conversations. And he said, Fred, when you're in your 70s, you just keep on keeping on. He said, when you're in your 80s, you just keep on keeping on. But he said, Fred, the 90s are different. And I thought, God grant. All right. So now let's move on to the 50s, and now software becomes important. So the big ideas of the 50s, and there are a lot of them, the most important was the closed subroutine and David Wheeler's calling sequence, the so-called Wheeler jump, and input-output libraries of subroutines available for users of the EDSAC, and the first symbolic assembler. And from my experience living without a symbolic assembler of any kind, having a symbolic assembler is a big difference. And so these generated 51, the most important book in the history of software. The preparation of programs. There also was a paper, of course, earlier about the machine proper, but this is the preparation of programs for an electronic digital computer. So Sir Morris is in the upper left corner, David Wheeler, who is one of the only computer scientists cited in someone else's Nobel lecture for his work doing the fast Fourier transform for Sir Martin Ryle's synthetic aperture astronomy, radio astronomy, and Stanley Gill. And now, here are the big ideas then of the 50s, besides symbolic assemblers and subroutines. Compilers, operating systems, terminals and communications, graphical displays, and block-structured programming. So the compiler story is very familiar to you. The first useful compiler was Fortran 56, and I remember what a big difference it was when that appeared on the machine. And it's very interesting because it's produced some of the best object code the compilers have ever produced. And the reason is Backus and company realized that if my compiler's code is slower than assembly code, people won't use it because computer time was very, very scarce and expensive. And therefore, it was a crew of mathematicians, and they worked very hard. And so the very first Fortran compiler produced running code that was faster than handwritten assembly code for almost all cases. Now, sometimes you could improve an inner loop by some devious trick, but in general, the reason Fortran was successful as a compiler was because it produced competitive runtime code, and that was when the programs typically would compile in 10 minutes and run for an hour, just the inverse of today's situation where they compile for an hour and run for 10 minutes. And then Grace Murray Hopper had designed an English-like language because she said for business purposes, people are going to need to be able to write in something familiar. Now, of course, the formality of a programming language is there no matter what you dress it with. But the Flowmatic idea introduced the notion of an English language compiler and really made it possible. And then she led the group that defined COBOL, and as many of you know, COBOL is still with us today, and so is Fortran. Now, on the building of an air defense system in the 50s against the bombers that were going to come over the pole meant that the MIT Whirlwind, which was a kind of a classical little von Neumann scientific computer with 12-bit word size, was designed as a prototype for the air defense system. And the air defense system was, in fact, put in place on a prototype region over Cape Cod in 1953. So it already had terminals, it already had communications, it already had graphical displays. Then the SAGE defense system was manufactured and installed on a large basis. A typical SAGE computer would occupy 2 stories of a blockhouse. It was a dual machine, so in case of trouble, it would switch over. It's the physically largest computer ever built. And there were 125 consoles for the people who controlled both the studying the radar for the inbound attack and controlling the weapon assignment for each of the individual interceptors and anti-aircraft systems. So much for the 50s. Big ideas of the 60s. Software engineering as engineering. And so there's Margaret's contribution, and then you will have heard and you will hear more from Brian Randell about the NATO conference of '68 and of '69. And as he will almost surely tell you, the '68 conference was a really innovative and really let's all get together and try to understand how to do this. And '69 was really let's fight for my side versus your side. And there were more than two sides, so it was a fractious conference. An important idea, there are two important ideas that came along then were the multiprogramming and time sharing. So Fritz Bauer conceived of the idea, as far as we can tell, of having the NATO conference, and he gave it the provocative name of software engineering techniques. It was provocative because the very notion, the term had been coined, but the very notion that writing programs was an engineering discipline was not generally accepted. And so the notion of naming the conference a software engineering conference was to get people to think about this strange fact. At the conference, the essential problem was the recognition of the software crisis. Now, I worked on operating system 360. I was in charge of the hardware from 61 till 64. And then we had the machines released into the factory, and my boss said, well, the operating system we're building is in trouble. Why don't you go over and run that for the year before you go to Chapel Hill? And so I had been through software crisis. We slipped, as far as useful delivery was concerned, we slipped a year. And so by 65, I already knew about the software engineering crisis. Didn't have to be told in 68. But other people had experienced it worldwide. Everybody building big systems, seems to have run into the fact that the growth is not linear. The effort, the complexity involves interactions, and interactions combine combinatorially. And so things that you thought you could extrapolate linearly, you couldn't. So the 68 conference, and Brian will tell you more, was about, okay, what do we do about the fact that we have so much trouble building big systems? Now, not everybody had trouble building, not everybody had failed big systems, but everybody had trouble building big systems. And then the 69 conference, the idea, and this is the book of the 69 conference, to give, and the 68th conference was mostly about how do you manage projects? And the 69 conference was about, okay, now what kind of techniques can we develop that will help improve the software engineering process? So it was essentially much more technical. And surprisingly enough, the conference about techniques was more fractious than the conference about politics and people management. That is surprising. Well, all right. Now, the first multiprogramming system that I know about was built by Ted Codd, and that name will be familiar to you for his later work on relational databases. But he built a system for the Stretch supercomputer. Now, Stretch was the world's fastest machine from 1961 to 1964. We built 9 of them. We sold them for $10 million apiece. It was sold to atomic energy commissions and to weather bureaus, principally worldwide, Britain, France, U.S. It stood about 5 feet high, 5 feet deep, 15 feet long. We built a 20-foot plug-in card for the National Security Agency that added on to it. But Ted, this was the first machine that had hardware for operating systems. So it had memory protection, it had programmable interrupt, it had a time clock that could do interrupt, and it had supervisory mode. And so Ted said, well, look, now that I've got this thing, I can build a multi-programming system which will enable one job when it's slowed down waiting for I/O for the CPU to go ahead and be doing computing on the other job. So the purpose of this was overlapping I/O and compute, not time sharing. But he built it and he made it work. So Christopher Strachey announced at the end of one conference, you know, it's time we ought to be able to build a multi-programming system. And Ted Codd stood up at the end of the conference and said, and we have one running. So it was very nice. Now, Ted did such a good job that I did the most useful thing I ever did at IBM, I think. and that on behalf of the company, and that is I paid to send him to graduate school to get a PhD, and that's where the relational database work was done. So, meanwhile, the idea of really making time-sharing systems was introduced at Manchester by Kilburn and Company, and first done on the Atlas computer that Manchester had built. This machine had paging, and it enabled their supervisor was designed to enable interactive debugging. So that's the ancestor, really, of all of today's operating systems. This gave the idea, meanwhile, at MIT, they were building one in competition for Corby on an IBM 7090, and that seemed like such a good idea that they would build a version of this called Multics, which was built for the GE 645, a machine that never had too much traction and didn't go too far. But Multics had many important ideas in it. It was a major project, and it came out, I think, 65. Whoops. Okay. Now, the other set of big ideas that I would point you to from the 60s were classes and inheritance and database systems and the whole idea of doing formal verification of programs. So the notion of classes and inheritance were introduced in the Simula 67 system by Kristen Nygaard and Ole Johnson Dahl, and we see them both here. Simula was designed as a simulation program, but this idea was so much more important and so much farther reaching that we don't even remember, especially Simula, but we do remember these fundamental concepts. Database systems, Charles Bachman designed a navigational database model in which the integrated data store, and Ted Codd came up 5 years later with the relational model, which is more popular today. The notion that we can prove things about theorems starts fairly early. So Bob Floyd wrote a paper assigning meanings to programs and showed that you could do proof, and then Tony Hoare came up 2 years later with an axiomatic basis for computer programming. So today, the really crucial programs, one has to formally verify the kernel, and this is true of airplane programs, and this is true of autocar programs, because no matter what we do, we cannot test all the bugs out of a programming system. So now we move on to the 70s. And here's some big ideas from the 70s. Information hiding, modules, abstract data types. The notion that we can build top-down by incremental refinement. Notice that some of these are conceptual ideas and some of these are process ideas. Inspections and software engineering management as a discipline. So David Parnas, who is a wonderfully provocative character for fun, came up with the idea of information hiding. And he and I had a long debate on this, and it's invited in the second edition of the Mythical Man Month. And he was right and I was wrong. And his basic idea was you ought to have a program divided into modules. The interface ought to be defined as to what the legitimate inputs are, what the expected outputs are, and what the valid operations are. And then how it's done inside the module should not be visible from the outside, no matter what you do. We had built the operating system using control blocks in which every part of the program consulted the same control blocks to get the shared data, and so you could update the shared information by updating the control block. But it turned out that different people would update the control blocks wrong and wouldn't necessarily set the signals right, and Parnas was right, and I was wrong. Now, Parnas's idea was then generalized, and Barbara Liskov had, I think, the first important paper in the abstract data types. And I love this little cartoon that says, "Sure, I got principles. You want to see my Liskov substitution?" All right. So that was a proposed mechanism she had for using the abstract data types. And this magazine picked up on that, the OOP girls. All right. Top-down, incremental build, and stepwise refinement. Harlan Mills was one of the great pioneers of the early software days with many important ideas, and one of them was incremental build. He said, and he was working principally with real-time systems, he said, build an inner loop that doesn't do anything, except it has stubs for calls. And then one by one, you populate the stubs, and you test at every stage. So this is a incremental build approach in which you know you're right all the time. And he said, go ahead and deliver to a customer the very first version of that that's populated enough to do anything useful for them. Why is that important? Because the customer will want to do things you didn't think of. And the customer will find ways to mess up your system, that misuse your system that you didn't think of. So the sooner you can get a prototype running system into the customer's hands, into the user's hands, the sooner you will get the feedback back. This principle is so important that today we understand that, and we still don't always practice it. Klaus Wirth came, and Klaus said, "How do you pronounce my name?" He said, if you call by name, it's Wirth. If you call by value, it's Worth. When I like that. Klaus proposed stepwise refinement as a different concept from incremental build. It's a notion in which you may start with a sketch of the whole program, and then stepwise you improve the sketches. One of the important ideas introduced at this time in process was inspections, and Michael Fagan proposed this, having a formal team of outside inspectors go through the code, reading it line by line out loud, working against a set of specific requirements. So part of this is getting a set of specific requirements. And then the team of auditors essentially look at the code to see if it satisfies the requirements, as well as to look at internal defects. I'm not sure the degree to which this is practiced today. I think it's an important idea. And then the other idea from this 70s period was it's beginning time to start realizing that this is a management problem. And some of you are familiar with my book on the Mythical Man Month, which essentially people say, look, why is that book still selling today? About 10,000 copies a year. It's been 43 years since that book came out. Is it obsolete? Yes, some of the chapters are absolutely, ludicrously obsolete, like how to get stuff into a 4K memory and so forth. And some of it is not ridiculously obsolete, and why? Because the book is not really about technology, it's really about people, and the people haven't changed very much. The stage keeps changing, but the script doesn't change much. The other important idea from the 70s, and Barry's here, we had a good conversation last night, I hope you'll get a chance to talk with him, is requirements verifying and validating. The verification is, am I getting the requirements right? That is, are they complete? Are they consistent? Is the thing that's being asked for feasible in terms of cost, testability, and validation? Am I building the right product at all? That's a really crucial one. And so, no silver bullet paper you're familiar with, and it says software is essentially hard to build. And I'm going to restate a statement I made in '85. There's no single development in technology or management which alone promises a 10 times gain in 10 years, and I'll state that in 2018, good for the next 10 years. And so that concludes me, and I will then aim you at some important resources. If you have not seen Grady Booch's ACM webinar on the history of software engineering that starts at the beginning and goes up to the current, you should. And then the most important literature is the book that includes Barry Beam's lifeline contributions, very important papers to development, software development research. I think there's probably no book that's more useful in today's software engineering than the book of Barry's collected papers. And the other one is Hoffman and Weiss's collected papers of David Parnas. So these two giants stand tall across the decades in terms of the depth of their thinking, the breadth of their thinking, and the clarity of their thinking. So I would encourage you, if you're going to read anything, read Beam and Parnas. And with that, let me conclude. Take questions.
Thank you very much, Fred, for that very nice tour through the history of software engineering. So we have time for questions. We have 2 microphones here in the front, and also a couple of microphones up there in the aisle up there. So please come forward to one of the mics if you'd like to ask Fred a question. Give people a little bit of time to head to the microphones.
Can I?
Sure.
Go ahead.
Here, yes. I would like to ask you, do you see that there will be some big change in the future in software engineering, thinking about the new technologies, AI and such, or it's repeating the same thing?
AI is going to change things, and we don't know how. The key to almost all the useful AI today is big data input. And the only big data we have today that is relevant is massive code bases. And how we harness that, I have no idea. But we will see that develop. And my skill as a prophet is very poor. Morris Wilkes' engineering judgment and what he said 50 years ago about technologies is just incredibly on track. I was amazed talking to him. But I'm not that good a prognosticator. I'll stand by my 10-year prediction, but I'll stop there.
Okay, we have a question over here.
Yeah, I was wondering the relevance of the decision when IBM was forced to unbundle their software from the hardware as part of the Federal Trade Commission court case. That seemed to me strategically very important because for the first time we actually got a market for software, which we hadn't really had until then. And how would you see that as being important?
Well, it did change everything in the sense of market, and it meant that there was a room for competitors, essentially, and therefore free players. I think that competitively, having competitors is a healthy thing for the development of a technology. From the point of view of IBM, it removed a lot of burden. It meant that IBM still had to support the products and had to maintain the software, but at least they could collect separate revenue for that and could identify then the revenue to cost return. Whereas before there was an unlimited demand for software and there was no reason for the customer to limit the demand. There was no price, okay? And so from the point of view of one responsible for building a system to satisfy thousands and thousands of customers across all kinds of applications, that's kind of frightening. And that was before unbundling. So, yeah.
I mean, an interesting corollary to that is that when IBM negotiated the deal with Microsoft to source DOS, they never asked for the source code. Because I believe at that time IBM thought, no, the money's all in the hardware. They'll never make money out of software.
Well, IBM's whole PC story is kind of sad to start with, from IBM's point of view. To give away the processor to Intel and to give away the operating system to Microsoft doesn't leave you a whole lot to collect money on.
Okay.
Okay, so first, thanks a lot for your presentation. It was really inspiring. See all the history of computer science unraveling under our eyes was fantastic. I once heard somebody saying that he who doesn't know history is condemned to make the same mistakes again.
Santayana, yes.
And so this is very important to collect the history of how we developed software. I have initiated a few years ago a project whose code name is Software Heritage. We are building the archive of every piece of software ever built. So my question for you is, do you believe some of the very important software systems you are mentioning here are still around somewhere? Is it still possible to find the source code of this? Do you think it is possible to collect it and make it available for people to study it?
I don't know, but I know where you would ask. There's the Computer History Museum in Mountain View, California, and they have a collection. And there's the Computer History Museum in Minnesota, and they are especially strong on collecting documents. The California one is stronger on artifacts, but they also collect code. So those are the places I would look for the materials to be archived, and whether you have any way to, whether you have the assemblers and whatnot to analyze the code, if you have the source code, I don't know. Okay.
Okay, so thanks a lot. I know very well then Schuster, so but the question was, for example, would IBM be open to share the source code?
I haven't been associated with IBM since 1965.
Okay.
I've worked as a consultant and on their technical committee, but I haven't had any management responsibility there.
Okay.
So I have no idea to what they're open to.
Okay, thanks anyway.
Okay, do we have a question in the back there? Nope. I don't see anybody else. Okay.
Okay.
Well, thank you once again, Fred, for a very enjoyable talk. And we have a nice memento of appreciation here for you, some nice Swedish chocolates that I hope you enjoy. I'm going to look for some of these myself. So. Okay.
I got it. All right.
Some help there?
Yeah, I'll need help with the steps.
Okay. Okay, can I help you down? Okay, yes. Okay, and this is okay.
Thank you. Okay, it is a distinct, in some ways incredible pleasure for me to introduce Margaret Hamilton. When you live your whole life, at least your whole professional life, knowing of a person, and then you finally get to meet them many years later, it is an incredible experience. I had exchanged, in the process of the last few months of setting up these keynotes, a number of emails with Margaret, and we spoke on the phone. But I got to meet her for the first time only yesterday, and I'm very happy about that. Margaret was already mentioned in Fred's keynote, so I will just say a few more words. In addition to the fact that she is the person who came up with the idea of naming the discipline software engineering as a way of giving it legitimacy. Margaret was actually a mathematics student who was looking to go on to graduate school when she decided to take an internship at MIT developing weather software. Unlike Fred, who was doing stuff in octal, Margaret was doing stuff in hexadecimal on the LGP30. And there she kind of caught the software bug, not the kind of bugs that crash software systems, but the kind of bug that all of us have caught that makes you fall in love with this discipline. Over time, Margaret came back to, after working at Lincoln Labs, came back to MIT to work on the NASA project, the Apollo project. And there she led a team that developed software for the onboard systems, for both the command and lander modules. And some of the things that we take for granted today came out actually from that project, or out of that project. And one of those things is the fact that the human actually is expected today to be fully integrated into the software systems. So they can talk to the systems and interact with whatever the system is doing, and the other way around. That wasn't always the case. It was their work on the Apollo software systems that actually came up with the idea that an astronaut can be interrupted with whatever they're doing by plopping up a display telling them, hey, something is about to happen that you should watch out for. Anyway, this resulted in some of the most remarkable achievements, I think, in human history to date, including, but not only restricted to, landing on the moon. And subsequently, Margaret's analysis of the various things that went on in these projects came up or resulted in a theory of systems development. Margaret, for her achievements, has been recognized in many different ways, from NASA, of course, but also she received the Presidential Medal of Freedom a couple of years ago. And to me, since I have kids, and I have a daughter who's looking to go into a scientific discipline, that will most likely, whether she likes it or not, involve software in significant ways. There was nothing cooler than seeing a Lego figure that came out earlier last year, I think, of Margaret Hamilton. And that actually meant something and will mean something to kids these days, which I think is absolutely fantastic. So again, it's my great pleasure to introduce Margaret, who will be our second keynoter today.
Thank you. When we ask developers who are looking for a better way to develop software, and we ask them what their most pressing issues are, they almost always list the same issues. They might state them slightly differently, but they all seem to have the same type of problems with, for example, integration. It's either too late, if at all. Also, their software is unreliable, even with extensive testing. And it costs too much and it takes too long. Why still not unlike 50 years ago when the field was brand new? So what to do? Most people would say it's impossible to do much, at least in the foreseeable future. Software by its very nature is destined to have these kinds of problems. But they used to say that 50 years ago as well. Nevertheless, I believe it is not impossible partly based on many of my own experiences, together with others throughout the last 60 years or so. Not as long as Fred, but 60 years is still enough to look back. I'll go through some of the software projects that I have been involved in with others, what I think has and what has not changed, lessons we've learned along the way, and what we have done about it and some implications for the future. Some of the observations I've made on the earlier experiences was we started with no field for software engineering. You were on your own, and knowledge, or lack thereof, was passed down from person to person. A manager hired you if you knew the commands on his computer's native language. I thought, you mean like knowing a set of English words would mean you could write a novel? Tricky programmers were admired, and organization was vulnerable when one left. Terms were undefined, leading to errors, misunderstandings, and drama. Some things are quite different then, some not. The life cycle process was not unlike today's traditional life cycle. It would, like, for example, the waterfall spiral or agile and others, going from requirements to coding, mostly manual still, to endless testing. The first project that I worked on was for Professor Lorenz at MIT in '59. I developed weather prediction applications in hexadecimal and binary. Known for his groundbreaking work in chaos theory, his love for software-related experimentation was contagious. We worked a lot on finding better techniques to make the computer go faster. Towards that end, we learned more about hardware and software relationships so we could make the software run on the right place on the drum. Errors were a nuisance, and each debug session took forever. My contribution was to recognize how long it would take to go through making a paper tape by the LGP30. So I got the idea that it could circumvent the process by taking a pencil with a very sharp point and poking a hole in the paper tape so that I could change a 0 to a 1, or putting Scotch tape over it to go back in the other direction. This saved considerable time. Another thing is we learned to spend more time up front on the hexadecimal, so we wouldn't waste all that time debugging from the front end all the way down to testing. Sage system was another interesting system that I worked on. It was at this time important not to make an error, because if you did, the computer told everyone about it. When it crashed, we heard loud siren-like and foghorn-like sounds throughout the building. And since it belonged to the programmer standing in front of the console, it was no secret. Operators and programmers would come running to find out whose program it was. And the crash site where the program halted could be found in a foot-long register on the console with its blinking and flashing lights. The next step was to write the contents of the register on a piece of paper. But the next challenge was keeping track of which program caused which crash, because there were so many pieces of paper floating around for each error. My solution was to have a Polaroid picture taken of each programmer posing next to his or her bug. One time, one computer operator called me at home at 4 a.m., and he said, "Margaret, something terrible has happened." And I said, "What's wrong?" He said, "Your program no longer sounds like a seashore." I got in the car and rushed to work. We'd found a new way to debug using sound. Again, debugging was time-consuming. There were absolutely no tools for finding errors. the 24-hour turnaround encouraged us much careful thought and playing computer at the front end. Again, a solution of getting closer to the front end to make better programs. There was a fascination with errors on my part. A never-ending pastime of mine was to look for more ways to understand what made a particular error or class of errors happen and how to prevent it in the future. SAGE definitely came with drama, especially having to do with errors. But this was only the beginning of what would come next, the Apollo onboard flight software project at MIT, under contract to NASA. The challenge was unique. Build man-rated software, meaning astronauts' lives were at stake. It had to work, and it had to work the first time. Not only did the software itself have to be ultra-reliable, but it would need to be able to detect an error and recover from it in real time. Learning was again by doing and being. Hardware engineers had come to the project with rules. We didn't. Problems had to be solved that never had been solved before, and at times we just made it up. Most developers were fearless and young, yet dedication and commitment a given. Managers, mostly from hardware backgrounds for whom software was a mystery, gave us total freedom and trust. There was no time to be a beginner. First, I started working on the unmanned missions, as we all did. At this time, the flight software was synchronous. We started with the primitive languages with a very few instructions, the block 1. The beginner's experience that I had, I remember going in and hearing all these engineers talking often, where one would say to the other, well, how did you solve that problem? And another one would say, I used the Agikugo method. And I thought, they keep mentioning it, and I don't know what it is. I can't tell them I don't know what this method is that everyone is using. So I finally got the courage, and I said, what is this method called the Agikugo method? And I found out it was eyeballing in German. The manned missions came next. And the onboard flight software was much more complex for the manned missions. It was an asynchronous system where higher priority jobs interrupted lower priority jobs based on every job's priority relative to every other job's priority. The developers manually assigned a unique priority to every process in the flight software to ensure that all events would take place in the correct order at the right time. It quickly became clear that no one and nothing is perfect, even astronauts. We were always searching for new ways to prepare for and recover from the unexpected, going from program-specific to system-wide protection. I remember one time I would take my daughter to work on nights and weekends, and she would watch me testing out the software using the astronauts' DSKY displays. She got very interested in wanting to play astronaut. So at this time, she started playing astronaut, and all of a sudden, the simulation crashed. I realized she had selected PO1, which was a pre-launch program, during flight. Well, mission phases were not allowed to share. They each took their own piece when they were due. But I started to worry about the debug session my daughter had, and she was maybe 6 years old at the time, thinking, what if the astronaut did what she just did? And I went to the management, NASA, and others about this, saying, I think we need to put a change in there, asking if it's the good time to be selecting PO1. They said, won't ever happen, just won't happen. The astronauts are well trained, they don't make mistakes. The very next mission, Apollo 8, this very thing happened, that PO1 was selected during flight, during mid-course. And it took hours to get it back up again, replacing all the data. And I should mention also, I did talk management into having a program note, since I was not able to talk them into putting the change into the program before Apollo 8. And the program note said, very simple, do not select PO1 during flight. Now, after this flight, everybody got together and said, I think we better put that change in for all future flights. This is what it looked like when we were supporting mission control in Houston. This is the SCAMA room at the MIT Instrumentation Lab. And here we are all supporting mission control and what to do. And this very well could have been the picture taken during Apollo 8. A mission not too far behind was Apollo 11. Here we are again, supporting Houston's mission control. Each mission was exciting, but Apollo 11 was special. We had never landed on the moon before. Everything was going perfectly until something totally unexpected happened. Just as the astronauts were about to land on the moon, the flight computer became overloaded. The software's priority displays of 1201 and 1202 alarms interrupted the astronauts' normal mission displays to warn them there was an emergency, allowing NASA's mission control to understand what was happening and alerting the astronauts to place the rendezvous radar switch back to the right position. It quickly became clear that the software not only informed everyone there was a hardware-related problem, but the software was compensating for it. The displays gave the astronauts a go, no-go decision, land or not land. With only minutes to spare, the decision was made to go for the landing. The rest is history. The Apollo 11's crew became the first humans to walk on the moon, and our software became the first software to run on the moon. Thank you. What happened during that time in Apollo 11 is the software's system software error detection and recovery mechanisms took over control. When the computer became overloaded, the restarts were triggered, the restarts in the software, keeping only the highest priority jobs going. I remember thinking, why isn't a multi-programming environment really like a distributed environment? Because after all, there's one program running, but other ones are sleeping at the same time. Isn't this going on in parallel? With this as a backdrop, the priority displays were created, changing the interface between the astronauts and the flight software from synchronous to asynchronous, the software and astronauts becoming parallel processes in a system of systems. It would not have been possible without an integrated system of systems and teams approach and contributions made by other groups to support our flight software, system software team, and making this happen. The hardware team at MIT changed their hardware, and the mission planning team in Houston changed their astronaut procedures, both working closely with us to accommodate the priority displays for both the CM and the LEM for any kind of emergency and throughout any mission. Mission control was well prepared, along with the astronauts, to know what to do if the priority displays interrupted the astronauts. Around the time when the manned missions were just about ready to happen, I began to worry a lot more about what if an error happens. An astronaut's life could be at stake. And I started to worry about what if there were an emergency? How do we tell the astronaut? We can't interrupt him at times. So I went to the hardware people to suggest that we put something into the system that would interrupt the astronauts' normal displays, replacing it with priority displays, telling them what's going on and giving them options. The hardware people said it's not possible. We can't do it. And I said, why is it not possible? And they said, because the hardware is not on all times. In fact, it's more off than on. And I said, then why can't you just leave it on? And the hardware people said, well, we can't do that. And I said, why? And they said, it's never been done before. So they went back, thought about it. They came back and said, I think we can do it. We're going to do it. Well, now somebody else comes along with a problem. Some of the systems guys said, you're trying to do something with parallel processing, and there are real problems to do what you're trying to do. The problem meaning when the astronaut's responding to the display, which display is he responding to, the normal displays or the priority displays? So then I had another problem. I went home and stayed up at least the whole night, and I came up with a solution which, for those of you who are experts in these areas, know that one could not have come up with a more primitive solution than I came up with. And the solution was, if a priority display comes up, the astronaut had to count to 5. And then we knew what display he was responding to. Well, they liked the solution, and they trained them on the solution. And sure enough, it was a good thing that they had it. Everything somehow seemed to relate to everything else, for better or to worse. A couple examples. I remember putting a change into the system software, and that night put it into the official assembly version, and all of a sudden there was a line at my door going around the hallway. Everybody's runs had crashed. The error was a mistake in the system software which impacted everybody. Then I came up with a solution to avoid this, and that was never to put your change on the official version until you tested it on online versions. So we all began to use the concept of offline versions first. Another thing is the very one way that one communicates can also cause or prevent crashes. So then we came up with the idea of daily memos, not emails going to 400 people, but hard copy memos being delivered by human beings to all the people that worked on the project. We then realized that we had problems with definition. What is an error? Who made the error? How do we decide who made the error? How do we know if the error is a catastrophic one or an FLT, a funny little thing? So then we had to go about deciding on these things. There was the opportunity to make every kind of error humanly possible, each with hidden secrets, on hindsight, a blessing in disguise. The task at hand was to develop the LEM and the CM software, including the system software shared between them, and the structure of the software that we call glue, that defined the relationships between and among mission phases. Updates were continuously submitted from hundreds of people over time in many releases. Making sure we had to make sure that everything would play together, that the software parts would interface to and work together, as well as with other systems, the hardware, the peopleware, and the missionware. We had a great handicap in that there was very little hardware time and space. So software experts prided themselves with tricky programming. Requirements were thrown over the wall by non-software experts to the software people. Their assumption was that all software programs would somehow interface together magically. Both of these groups were responsible for some very interesting errors. As I mentioned earlier, we had to share data, erasables we call them, between mission phases. And in the multi-programming environment, there could be up to 8 tasks based on timing and 7 jobs based on priority going at the same time. These were great places to make errors. We evolved in our software engineering rules with each new relevant discovery, while top management rules from NASA went from complete freedom to bureaucratic overkill. It was not possible, certainly not practical, to test the software by flying a real mission. We came up with 6 formal levels of testing. They were a mix of simulations, mixing hardware and digital simulations of every and all aspects of a mission, which included man-in-the-loop simulations, real or simulated human interactions, making sure that a complete mission from start to finish would behave exactly as expected. Of course, assuming the simulations themselves were ultra-reliable. I'm happy to say that there were no onboard flight software errors ever known to occur during flight. Having been through these experiences, one could not help but learn from them. And with initial funding from NASA and DoD, we performed an empirical study of the Apollo effort. Our analysis took on multiple dimensions, not just for space missions, but systems in general. We then listed all the things that we thought were important on previous missions, one of them being always ask what if, always expect the unexpected. We learned that systems are asynchronous, distributed, and event-driven in nature, and that this should be reflected in the language to define them and the tools to build them. Once having done so, there's no longer a need to explicitly define schedules of when events occur. Simply by describing interactions between objects, the schedule of events is inherently defined. Most interesting of all were the errors which were found during pre-flight testing of the software. They were full of surprises. They told us what to do, and they told us where to go. We concentrated on 3 categories. One was interface errors, which are data timing and priority conflicts. Errors found by manual means, in other words, the Eige-Kugel method, and previously existing errors, which were the most subtle and hardest to find. Categorizing the errors led to a systems theory of control that has continued to evolve based on lessons learned from Apollo and later projects. Its axioms led to a set of allowable patterns that led to a language evolving together with its automation and preventative development paradigm, development before the fact. The interface errors were especially important because the majority of errors were interface errors. Along the way, it hit us one day that traditional system engineering and software development languages and their environments support users in fixing wrong things up. In other words, after the fact, rather than in doing things in the right way in the first place, before the fact. And that a system defined with this language, which had been derived from the systems theory of control as its foundation, has properties that inherently support its own development before the fact. And unlike traditional languages, it is based on a preventative philosophy. Instead of finding more ways to test for errors late into the life cycle, find ways not to allow them in the first place just by the way a system is defined. With the language, every system took on certain properties defined from the very beginning to inherently integrate all of its parts right from the start, and maximizing its own reliability, capitalizing on its parallelism, and maximizing the potential for its own reuse, its own automation and evolution. Every system with the language is defined with properties of control, a formalism for representing the mathematics of systems. The language is based on a set of axioms and formal rules for their application. We began to use it in just about any kind of system, whether it was an application or whether it was hardware or software or some kind of architecture. The language is syntax independent, implementation independent, and architecture independent. It's the semantics is what counts. Unlike a formal language that is mathematically based but limited in scope from a practical standpoint, for example, the size of the system, it USL extends traditional mathematics with unique concept control. The process that we began to go through in building a system, now that we had the language, we created its automation, is to define a model with the language, analyze automatically, making sure that it was used correctly, the language, and generate automatically much of the design and all of the code, production ready. Then execute the model, and if it wasn't working, go back through the process and redefine until you finally have it ready to deliver. The philosophy, USL's philosophy, is that reliable systems are defined in terms of reliable systems. You use only reliable systems as building blocks. Once that you've shown to be reliable, integrate those with systems using reliable systems. And the result is a system which is reliable. And so we began to build a library where everything was derived in terms of something that had already been developed that was already known to be reliable. Every system is defined with function maps called F maps and type maps called T maps. Function maps define the relationships between all the functions. Type maps define all the relationships between the types. F maps and T maps are inherently integrated. And every map, every F map, every T map is defined in terms of 3 primitive control structures. The 3 primitive control structures have to do with dependent relationships, independent relationships, and alternative relationships. And each control structure has its own set of rules which have been derived from the axioms. Here we have a system called Make a Table, which shows the doing side of the system, and we have its type of data called table, which is the being side. We have the doing and the being. Every function is defined in terms of one of the primitive control structures, one of the 3 primitives. The systems defined in terms of their primitive control structures result in properties for real-time distributed environments. So for example, we could find all concurrent patterns in a system, and every object ends up having a unique priority. A system is defined from the very beginning to inherently maximize the potential for its reuse. So we started with the reusables of the 3 primitive control structures, but now we can build a non-primitive control structure in terms of the primitives. So we have a new system here called co-include. It doesn't matter what it does. It was just a pattern that would happen over and over again, and we thought, why keep doing it over again? Let's make a new reusable. So we did that. Now we found another pattern that kept happening over and over again. This case, it was for an asynchronous or synchronous behavior. It's defined in terms of the primitives and the new one we just created called co-include. And here we see a system now taking advantage of the library's new structures. We do this in F maps and in T maps. Here we see a system that's a little bit more complicated than one we showed before. It's part of a manufacturing shop floor where they're making a robot arm. We see several T maps and several F maps describing a small piece of this system. Here's a system that basically shows the robot that was manufactured. And he's sensing things. He's supposed to look out there and find out where there's danger. For example, thunderstorms are considered to be dangerous. Now he has to bypass that danger. And if he doesn't, it turns into a reject and there's no longer a robot. Otherwise, he goes on and starts sensing other things. So we've talked about definitions, modeling definitions. We call that the definition space of F maps and T maps. An instantiation of a T map is an object map. An instantiation of an F map is an execution map. Now, when it's running in the operating environment, They're actually maps that you can watch if you see it on a disky, actually a graphics, and you can see how the maps are inherited from the definition from which they came. Now that we could define a system and we analyze it to make sure we did it correctly, we have a choice. We either go to generate the code, if it's software, it could actually be ready to execute, or we could go to the interpretive part of the language and execute it, for example, for system engineering simulation. One of the most powerful aspects is the degree to which reuse inherently takes place. I've mentioned a few forms of it, but there are many others. One might ask, how can one build a more reliable system and at the same time increase the productivity in building it? Unlike the traditional test-to-death philosophy, less testing needed with the use of each new before-the-fact capability. Correct use of the language eliminates the majority of errors, including all interface errors and their derivatives. The analyzer hunts down the errors resulting from its incorrect use. Then we have the generator, which generates many different kinds of things to help debugging, but it also generates much of the design and all of the code. Maintenance shares the same benefits as development. The developer doesn't ever need to change the code. Developer only changes the specification or the definition. We continue to discover new properties in these kind of systems and their derivatives just by the way a system is defined. Thing I did not mention before, the way maximum reuse is obtained is that we've talked about deriving reusables, but much of it is also inherent. A system's definition provides input to and services the basis for USL's automation to inherit and pass on the definition's properties of control to the system's derivatives. So if you have a definition that has these properties, it's going to generate code that also has its properties. For example, no interface errors. Properties of control are built into the language that come along for the ride. With the language to define it, software can be developed with built-in reliability and built-in productivity throughout its life cycle. And much of what seems counterintuitive with traditional approaches becomes intuitive. Less testing becomes necessary with each new before-the-fact capability. A language without preconceived notions, the more reliable the system, the higher the productivity in its development. And unlike what has been in large part a manual process or automation to support the manual process, automation can do the real work. The language's own automation, a large, very large system, millions of lines of code in its own right, has been completely defined with, and it continues to generate and regenerate itself. This is possible because of the mathematical foundation behind USL. It also takes roots from other real-world systems, formal methods, formal linguistics, and so forth, and it has evolved over many decades. It's always stood its own when put to test in various environments, academic, government, and commercial. It helps to suspend any and all preconceived notions when first introduced to this language because it's a world unto itself, a different way to think about systems. So along the way, it becomes clear that many aspects of the pressing issues can be addressed with a preventative approach, ultimately eliminated altogether. Several software engineers' tasks become no longer needed. What we do about what we have learned, however, depends on how ready and how open developers are to a change in how we build software. It's been tested in several research and early user applications in diverse environments, including comparisons made by each of these kinds of environments. What's interesting is the commercial people call it comparisons. The academics people call it studies or experiments. But Lockheed Martin and some of the aerospace people, they called it a shootout. Unique criteria for each study. Comparisons are conducted by the government agencies, industry and academic organizations, refereed by third-party observers or by the agency sponsoring the competition. It tested it from initial establishment of system functional requirements through operational validated code. USL did not disappoint. In fact, the larger and the more complex the system, the better the results. The errors showed us how we can do without them, but they also led us to a language where each of its definitions inherently replaces what used to be aspects of the system's own life cycle, or serves as the input for the language's automation of what used to be manual processes and the system's own life cycle, or results in many parts of the system's own life cycle no longer needed. A language that, by the very way a system is defined, can serve as a software engineer in its own right. A language with a preventative paradigm that leads before the fact to the future. Thank you. Thank you. Questions?
Okay, I guess I'm back online. Thank you, Margaret, for this wonderful keynote. We have time for questions. Again, the microphones are in the front, so people will have to walk to them. And I see Diomedes is already.
I have a question here at the back. Hi.
Where are you? Oh,
okay.
Go ahead.
Hi, so this is Bashar Nusseibeh from Lero and the Open University in the UK. So I don't actually have a question. I have just one comment. I'd like to thank you for an outstanding keynote, and you and Fred Brooks. And I think every software engineering researcher and student should listen to these lectures once, twice, and many times and share them. I think that was a fantastic contribution. Thank you very much.
Thank you.
Diomedes Pinelis, AUEB. Based on your description, you said how you moved from complete freedom to bureaucratic overkill. Based on your experience, how would you recommend to strike the balance between the two? Because this is something we are continuously facing as a profession.
I've not found an answer to that one.
Thank you.
There's a question over here.
Hello. My question over here is...
Margaret, on this
Where?
side. On the left side.
Oh.
I'm here.
On the floor, right
yes.
there.
Oh, I'm still not sure.
My question is regarding all the studies you did in the projects to understand what makes the clock tick to be able to build these systems, and the importance of engineers understanding the basic science and these systems. And there's been this myth of, for instance, Apollo 13 being able to pull it off just in a room, but there were all these studies being done and all the things you learned in order to pull the whole thing off. And if you might have a comment about that and all the efforts you did to be able to get it together.
I don't quite understand which part you're referring to.
I'm referring to all the work that you could then, in order to build the software and so on, there was all these studies that you
Yes.
could pull from, and you learned yourself and all the materials. It seems to be like there is a myth, a popular myth about it's just you did things on the spot, but you had all these things done and worked on before.
Yes. And every single study, we would learn brand new things. Everything we did ourselves, we would keep studying and finding things that, for example, made errors and why, and go back and make changes based on that. But we learned so much from the customers who were doing the studies, and that helped improve what they were doing, and it helped improve what we were doing.
And you were curious engineers, and you found out things that you couldn't plan for, and that you could then build on, as
Yes.
I understand you. Thank you.
Thank you.
There's a question in the back, and there are going to be a couple more after that.
Hi, Margaret. This is Rishina Hoda from the University of Auckland, New Zealand. It was a long, long flight, and this has made it totally worth it. Thank you so much.
Please,
I'm
all
here.
the way up
Hi.
there.
Yes, great.
So I have a question and a comment first. Can I please thank you on behalf of all the women in engineering for being such a role model? You can just see from the...
Thank you. Thank you.
You can just see the small difference right now in the number of women who have actually chosen to stand up and make a comment and ask a question right now. That's the difference you make. The question I have is, what has been your experience of seeing any change at all in the experiences of women in software engineering over these years?
Well, that's a good question, and I've struggled with finding a good answer. But in a way, I find parallels between system engineering and the problem, because every time something negative happens, it goes throughout the system. But every time something positive happens, it also does that. So it's much more up to people who are in leadership positions, whether they're running a company or a country, to try to make that balance go more towards the positive. But when people come up and say, well, what can I do about women? Paying them higher. What can we do about the problem? And I say to them, just pay them equal wages. Don't talk about it, just do it. And I never understand why it is a problem, but it's just getting things going. It's a bootstrap.
That's great. Awesome. Thank you so much.
Thank you. Thank you.
Hello, Frances Powlish from Siemens Healthineers.
Frances.
So I really appreciated the fantastic presentation, so I'm very glad to have heard it. My question concerns the topic of things like safety critical systems. A lot of times there's a certification on a per product basis to show, for example, requirements traceability in the system, and it's always done on a per product basis. Are there experiences with using your systems in the USL in the certification, like for FAA or for other kinds of certification authorities, to say if it's done with this kind of methods that it has an easier way to go through the certification process?
Yes, we had to demonstrate that type of thing to several government agencies. And one agency we did it for, we had to show going from requirements, in fact, it was a competition. They had gone down from many, many vendors at the time, down to 4. And our product was one of them. We had to show, they were all the government restrictions, from requirements, definition, specification, generating code, and then making sure it worked. And since our system was able to generate to one of a possible set of languages, we had to end up in this project, this with Lockheed Martin involved, MITRE, and many organizations, maybe 80. We had to demonstrate this, and we were really knowledgeable of Ada, but many other languages we had generated. And Ada turned out to be much slower to get to that point. So we first generated everything in C to prove it worked. And then we went back and then we generated Ada. But we then were asked to pass all the certification processes to prove specification matched requirements and the code, the specification, and so forth.
So very much
A, B, and
up,
C
yeah.
specs.
Mm-hmm. But it very much speeded up the process of going through that certification.
Well, we did a trick to speed it up, right, by generating the C first. But we did do what they asked. We just had our own way of getting there. Did it speed up the process? I hate to say I'm not sure, but I'm not sure.
Okay, thank you very much.
Thank you.
There is a question in the center back.
Here. Hi, I'm Yixue from University of Southern California. First of all, I really want to thank you for such an inspirational talk and all the great work you've done. So my question is, it's really fascinating to see how those concepts we take for granted nowadays were actually came up with like long, not really that long, I mean less than 100 years ago. but like, I think those fundamental steps that you took, and that's the biggest value, you know, all the coming up with those things like offline testing and daily memos.
Yes.
So thank you so much for that. So my question is, so in your opinion, like nowadays in the current state of the art of software engineering, are there any still concepts missing or any fundamental research should be done? Because most of the research are mostly like, you know, improvement of something, but
Yes.
like, are there any foundation work still missing in your opinion?
Yes.
And
Yes.
what are they?
What are they? Well, I think it's not unlike with any other large system, complex system. I think it's the same kind of problems that we had on maybe a smaller scale with Apollo and others. But it all had to do with interface errors. I mean, we learned about the errors that we found. There were many different kinds, which made it really invaluable to us, what we did learn. But we learned that interface problems, whether it was on Apollo or later systems, that the interface errors accounted for about 3/4 or more of the problems. And people don't really tend to have the kind of methods that would prevent that from happening up front in at least traditional system environments. And I know that there's been errors in cars and elsewhere where probably more often than not it has been an interface error that causes a crash either of the software or of the car.
Thank you.
Okay. There's a question here, then in the back, then here. I'm keeping track, don't worry.
Thank you. Okay, thank you. Tiziana Margaria, University of Limerick and Lero. I'm here.
Hi.
Hi.
You're easy.
Yes. So first of all, I mean, thanks and complimentation for the achievement. I love the language that you developed. We've been trying to work in that direction for 20 years now, actually starting with a project with Siemens. And the idea of having these behaviors and the types interact
Yes.
and be kept consistent over evolution was actually stunning at that time for the mistakes that didn't happen anymore in the testing. It was just going through the breeze through the testing. So now with the educator hat on my head, I'm trying actually to teach these things to first and second year students. It's amazing the kind of uphill march that I have in, let's say, advocating this unorthodox way of describing things, which is architecture agnostic and towards preventing instead of fixing, as you were saying. I'm for well-being instead of sick care.
Yes.
Do you have experience in uptake in education of this kind of approach that you have?
What we think is the most important thing is to work on coming up with the education that is needed to be able to make a change this substantial in the way that people are doing things today. That requires a lot of resources to make that happen. Any new projects, for example, new languages like with Java when it came up, and other languages, requires all types of education, bringing it into the universities, and having the right courses available. Yes, we've thought of it a lot.
Well, I would be interested to follow up and see what was your experience and try to tie it in ours in Ireland.
What was the experience in?
I would be interested in following up and maybe discuss about that experience because it could benefit us.
Yes, yes.
Okay,
thank you.
There is a question all the way up in the back.
Hi. I'm Cyril Arthur from KTH in Stockholm. And I think in industry...
Where is he coming?
Up here.
Right there.
Oh, okay, thank you.
Most companies nowadays, they still develop software by just hacking it together and then debugging it until it sort of works.
Yes.
So why do more formal and model-based approaches don't make their way into practice so much? What holds them back?
What holds them back? If I had the answer to that question, I'd be in a very different situation than I am now with respect to this. It's not easy to get any new ideas out there. It requires a substantial investment. It's called advertising in some ways, but you want to get the word out there and get people wanting to do it. I think, you know, it's very difficult with new languages, with new tools. Again, they have to be supported by somebody large enough to make that happen. Now, you may be bringing up things about large organizations trying things, and I don't know why something failed or did not in those cases. But I do know what it has taken for us to educate people along the way. And one thing we found is that it's much easier to educate the younger-minded people, the younger minds, which could either be kids coming out of school who'll pick it up very quickly, or older people with younger minds.
There's a question right there.
Yes.
First, thank you very much for that talk.
Thank you.
I have two questions. The first question is, you had increasing work in terms of software. How did you recruit new people? What did you look for when you wanted a new person to join your team?
Well, when we first hired a lot of people, some people came with experience with software. Other people were philosophers, artists, but creative people that enjoyed the creative part. And they turned out to be extra good software developers.
The second part was there a need to have a deep understanding of the domain? The space of mission is a completely new domain. How did you acquire the skill of what's needed to make it successful?
Well, I do know that we went around to Wrexham organization, and we sat there and actually asked questions about their environment because they wanted us to model the whole corporation, or at least parts of it. And how we learned about it was not intentional, was in modeling their environment and helping them to do it. The USL type of language helped us to ask the right questions. What are the inputs? What are the outputs? And we discovered, for example, when people modeled their systems, they didn't include decisions that were made. So they were not getting the results they were expecting. But that was one way of learning together with the customer, they learning how to do the modeling, we learning the domain. So that's one example.
Thank you.
Okay. There's another question in the back, and then Gregor will get to you. Danny?
Yeah, so
he's,
here.
again, center back. Maybe you raise your arm?
Yes.
Right there.
Hello, this is Danny Dick from Oregon State. I'm just full of gratitude. As a software engineering field, we are standing on the shoulders of giants like yourself and Fred Brooks and Dave Parnas and others. So I'm just full of gratitude.
Thank you.
So my question is, as we are passing the baton from one generation to another generation, we want the generation coming after us to go higher and to reach higher and to go further than we did and we are going. Can you pass in, maybe distill one or two lessons, keep takeaways for things that we should do or we should not do as we are enabling the next generation of software engineering scientists and practitioners?
Well, one thing that stands, a couple of things. One is learn from the errors that are made. And the more errors you make and the more kinds, the better off you are. But of course, there's a catch-22 there. But the point is by learning from them, not just how to prevent a particular kind of error, but all the errors that took place within the system and what you can do about not having those problems in the future, however you go about it. And also working towards the front end. Whatever you can do up front, do it then. Don't wait until later, until the errors have a time to grow. I think that can be done in any system, having that sort of a preventative approach towards finding how to do things better.
Thank you.
Okay. There's a question right here.
It's me.
Yes.
Okay, it's easy. So my name is Engels Gregor. Nowadays we discuss a lot about how far can we go with developing software systems. And my question may be quite personal. How did you feel in the time when you were building software there for astronauts? Was you scared that maybe your software fails and the astronauts are killed? So how did you cope with this difficult problem, being responsible for human life?
Going in and finding ways to detect errors in real time and recovering from them in every way possible. Do everything you can when you expect the unexpected and to do something about it.
Okay, yeah, thank you.
Same location.
Hello, Ita Richardson from the University of Limerick and Lero. Not only have I talked about you in the past, I've talked about the young woman who contacted Lego because there were no female Lego figures. So I think it's just great to have you here today, and thank you for the talk. One thing struck me as you were talking. You mentioned at one point that software people were allowed to do what they were doing because nobody understood what they were doing. And then you talked about, the astronauts as such were your users, your customers, who really did understand the domain and were on a scientific level. But I do wonder sometimes, do we as software engineers still take advantage of the fact that a lot of users still don't know what we're doing? And I'm wondering if there's something in the user community that should, we talk a bit about this interdisciplinarity, bringing users on board, but do we need to educate the user community in what we're doing, or do we actually get away without doing that and enjoy getting away with it?
Well, that's not an easy question to answer, but I think because we work with people for many years, of how to model their systems, we can't help but learn about what each other is doing. And so that's how we've been dealing with it by default.
Okay. Same place.
Right.
I think we have time for one more question.
Right.
So.
Thank you for an amazing talk. And my question would be, how would you compare approach with formal modeling upfront versus, how do you say, the startup fail-fast strategy? And which is better in which type of projects?
I think modeling the definition up front is most important for large, complex systems, but also how large is large. I think we end up doing a lot of small ones to make the big ones, of course, but yeah. There's rapid prototyping, but we do rapid prototyping even with the formal approach. And then building the systems that can then use each other on the build-up. Ultimately, I'd have to say the more formal approach. To be true to myself.
Thank you.
Okay, now really the final question. And afterwards, Margaret will be around if you have any other questions, but we've already asked so many, so please go ahead.
You mentioned in your talk about cowboys and that cowboy approach, and still teaching now with all of the things we've learnt from 50 years. The students, many of the students in computer science are still cowboys, and they want to know the intricacies and they want to have the trickiest code. But you had a different approach, and I wonder how that comes about and what was different about you that you didn't want to be in that space of the cowboys.
Well, I think doctoring up the paper tape was an example of my first experience at hacking. But I did find out quickly it was an error-prone process. But it is true that programmers were admired for being tricky in the old days. But then, now I think people are more admired for doing it right. And on Apollo, if something was creatively done and did some elegant things that it did, that became more the norm than the tricky programming.
Okay. Because we seem to have code going out and it's buggy, and we have patches and patches and
Yes.
patches. So I don't know if we've really got past it being, you know, let's give you the next feature, but there might still be problems.
Yes, well, the thing is, if you're able to generate the code so that it integrates everything, in this way of doing things, you can't add on code after the fact, because then you'd run over it if you tried to generate the rest. So by going back to the original spec or definition, you can just go through the development process even for maintenance. And then you don't keep adding patches. You can't continue if you add patches. Using that approach, I mean.
I also wonder that perhaps there was something nurturing in you. You talk about taking your daughter, and with your children, you're trying to work out ways for them to not make errors again. And perhaps that's the female touch that comes into your approach to programming.
Is that used with children, you're saying, or did I use it?
Well, your daughter presses a button that
Yeah.
fixes the system. You think, okay, how can I stop that happening again?
Yeah. Well, I guess when it came to my daughter, she has a mind of her own. But she has a creative mind. And I don't know if that's answering your question, but I guess being a worrier with respect to the astronauts, when you know that the system had to work and it had to work the first time, that's pretty scary for somebody just being young and going into the field, that you were responsible for this kind of thing possibly happening. And that's enough to make you want to do it right if you can. One does not want to picture the Boston Globe or the Boston Herald having headlines about the flight that took place the night before.
Excellent, thank you.
Okay. Yeah. All right. Thank you all so much for all the questions, and special thanks to Margaret for handling them so graciously. Also, a small token of appreciation, just some Swedish chocolates.
Oh, thank you.
Thank you so much.
Thank you.
Thank you.
Oh, I have here.
Okay, that concludes the morning keynotes.
Okay.